Hi, welcome to Module 6. Module 6, we're going to talk about section 6.4 and 6.5. We're going to talk about a lot of different types of functions. There's a lot packed into this module, and it's definitely a lot of algebra. So what we're going to talk about today, you might see spread across, maybe a month or two in an algebra course, and we are just going to do it in one module. So it's really going to be pared down to just the most important tidbits of each function. We're not going to learn every single, in and out for every single type of graph, but we're just going to touch on the most important ones. And since we're going to do some graphing in this module, I do think using some sort of graphing calculator, graphing software could be helpful. So definitely don't run out and buy a graphing calculator, but if you have one, you can use it. And if you don't have one, I'm going to show you real quick where you can find a free graphing software that can be handy. So it's called Desmos. So just Google Desmos, and then if you click on their site, you just click on graphing calculator, and then it's super simple. I actually like this in many ways better than a graphing calculator even. So all you have to do is type in your graph in the box. So if I want to graph y equals x plus 4 equals x plus 4, you just type it in. If you want to graph something that's squared, for example, you can press this little calculator button over here, and then there's a squared function. You've got square roots, absolute value, anything that you'll need for this module, you've got. And again, it's free, so this is something to keep handy. I would actually look and bring this up right now before you jump into the rest of the video, and then that way you'll have it when you need it. So I'm just going to minimize that. Let's just jump into section 6.4. So before we talk about all the different types of functions and what a function is, whoops, there we go. Let's talk about what a relation is. So a relation is a rule matching up two sets of objects. And the reason we have to talk about what a relation is because the definition of a function sort of has relation as part of it. So we need to step back and talk about a relation first before we jump in and talk about what a function is. So it's a rule that matches one set up with another. And so a couple of examples. So in this first example, set A, we've got a list of ordered pairs where the company name is paired up with its stock abbreviation. Okay. In the second example, we've got a list of ordered pairs like you traditionally see where you've got an x value paired up with a y value. There's no rhyme or reason for this list of numbers. This is just a made-up example to show you that this is an example of a relation. When you have a relation where every x value, which is that first coordinate, only goes with one y, then we call it a function. Okay, so let me say that again. Every x value or first coordinate only goes with one y. So as an example, let's look at A and B here and decide if these are functions. So every x, so every company only has one stock abbreviation. That would be true. So this would be a function. For the second example, it looks like in this example, this would not be a function. And if you're not sure, this would be a great time to pause the video and take a look at this and see if you can figure it out for yourself. So every x needs to go with only one y. And the reason that this is not a function, I'll highlight it for you here. 3, we have 3 going with 9, and we have 3 also going with 3. So that x value 3 is matched with two different y's, and that means this is not a function. Okay, so let's go ahead and do some more examples. Practice identifying functions. So we're going to do this section right here. Which of the following equations represent functions? So this would be a great place to pause the video and try these on your own. So for the graphs here, you can do one of two things, or for the equations rather. You can graph them and look at a picture, and I'll show you what that picture, how we can identify parts of a picture that help us decide if it's a function or not. Or you can just look at the equation and just ask yourself, okay, is it possible for me to plug in an x and have two different y values just by the nature of what the equation is doing with those variables. So let's do the first one. This one's the simplest. So let's look and see if any x goes with a different y. And one quick way is just to look and see if any of these x's repeat. So I've got a 5, a -3, 11, a -10, a square root of 3. Those are all different x's. So I'm not going to have any example here where I have the same x going with a different y. So notice my example up here with set B. I had 3. I had that listed twice and I had it going with different y's. So that doesn't happen here. So I'm going to say, yes, this is a function because every x goes with one y. Now it's okay. Notice there are repeat y values, and I did this on purpose just so that we could see an example of the different kinds of repetition. So there, 10 is repeated. Okay, it goes with different x values, but the key here is we don't want one x going with different y's. It's okay to have different x's going with the same y. And if we looked at a graph of this, let's think about what this would look like if we graphed this function. So if we call this x and y, if we plotted 5, 10, okay, if we plotted -3, 10, if we plotted 11, 10, and I'm just doing a quick sketch, -10, 10, just estimate, and square root of 3, 10. So that'd be a little bit less than 2. Okay, notice that they all line up. Okay, you can even connect them and make a horizontal line. That is okay. That means this is a function. One test that you can do, it's called the vertical line test. This is the test that helps you decide if a graph represents a function or not. The vertical line test basically says that if you draw a bunch of vertical lines through your picture, and if it ever crosses the graph more than once, it's not a function. So when I did that here, it never crosses that blue line more than one time, and so we consider this a function. Now, in contrast, let me show you another example. I think this is one of those topics where lots of examples are needed here. If we look at that example up here, this set B that I said was not a function, if I were to graph those points, so I would have 9, 0. So 9, 0, -3, 1, 3, 9, -1, 5, 1, 2, 3, 4, 5, and then 3, 3. In this case, if I did my vertical line test, I start drawing my vertical lines and I ask myself, am I ever going to cross through 2 points at once? And for this one, I do. I cross there and I cross there. So again, if I have the same x going with more than one y value, then that means when I draw a vertical line, it's going to cross it twice. So this shows that that is not a function. Let's look at example B, so y equals x squared. So if we think about the type of what this equation does, if we ever plug in an x, so if I'm taking a number and I plug it in for x, if I square that number, am I ever going to get two different answers when I square something? So for example, if I do, and I could even do a quick table of values on the left-hand side for this one, so if I do x and then we'll do y equals x squared. So if I plug in, let's say 0, 0 squared is 0. If I plug in 1, 1 squared is 1. If I plug in 2, 2 squared is 4, and so on. So I'm never going to get more than one y value, and actually I should probably just label that column y. So I'm going to say, yes, this is a function. This is a point too, if you're a visual person, if you want to pull up that graphing software and you want to do y equals x squared, you can look at the picture. And I can't write on this, my pen doesn't allow me to write on web pages, but if you think about, I'll use my mouse, if you start drawing those vertical lines, it's going to hit the function, but will that vertical line ever hit that function more than once? And the answer is no, and so that's another just a confirmation that that's a function. Okay, so for this next one, same thing. This is actually really similar. if you plug in numbers for x, you've got x here and then x squared, will you ever get a different y value? This is called a quadratic function. Anytime you have a x squared, and it's possible to also have an x, but nothing greater, we call this a quadratic function, which is going to give us a parabola, that U-shaped graph, and we'll talk about this a little bit more later on. But let's take a look at what that graph would look like as well. So and this is the benefit of this graphing software, if you used a graphing calculator, you would actually have to solve this for y, but we don't even need to with this. So I'm going to use the square button, and then plus y minus 2x equals 5, and then you can see it's a U-shaped graph that faces down, and if you were to do the vertical line test, I would just continue to draw vertical lines, and you could even look at the vertical lines on the grid. Never do these vertical lines cross this graph, the red line or red curve, more than once. So I'm going to say that this is also a function. Whoops, we're going to stay, and I'm going to minimize. There we go. Okay, so we're going to say yes, a function. And one thing to think about is at what point, or what type of function, or what type of what could I do to a variable to make it have more than one output? And one of the functions that does that is, well, it's not considered a function, but one operation, that's the word I'm thinking of, one operation that does this is the absolute value. And when you take an absolute value of a number, you end up getting two answers. So for example, the absolute value of -4, well, sometimes you do. Actually, let me step back. You don't get two answers, but what it allows the graph to look like is it's possible in this case to get a graph where you could get two different outputs. So let me actually show you what that would look like. So let's do an example. So the absolute value of -4 is 4. The absolute value means the distance from 0. So the absolute value of 4 is 4. So I put in two different inputs, but I get the same output there. So watch what happens when I look at the graph x equals the absolute value of y. I'm going to look at the picture of that first. So I'm going to pull up my Desmos, and I'm going to type in x equals, and I'm going to go down here, absolute value of y. And then I'm going to look at the graph, and you can move the graph around. If you look at this graph, it looks like a sideways V. You see how if I were to draw a vertical line, I would hit it here, and then I would also hit it here. Or for example, we can actually look at the coordinate pair. So if I look at this mark right here on the x-axis, this is 1. I've got the point 1, 1, and I also have the point 1, -1. So there are two y values for the same x of x equals 1, and I'll show you, I'll write that down in the notes too. So if I were to say, in this case, the absolute value of 1 is 1 and the absolute value of -1 is 1, and so this is not a function because 1x corresponds with two different y values. And we could also see that on the picture. So it's not necessary with these kind of problems to go through both different ways by looking at the function and looking at the picture. If one speaks to you, better than the other, then just use that method. So if you just want to look at the picture, then just look at the picture. If looking at the equation helps you see it, then just look at the equation. Or if you're not sure, then you could look at both. So we're going to jump down to the function notation part. So you may have seen function notation before. So function notation is anytime you see this like f, we call this f of x or g of x. But let's start at the beginning. So if we have this equation, y equals x squared, it represents a function. So we did this example earlier that relates these variables x and y. We call the x the And maybe you remember. If you remember, go ahead and write it down. So we call the x the what kind of variable? It's the independent variable. And we call the y the dependent variable. Because its value depends on the choice of x. So we're choosing the x, we plug it in, and that determines what y we get out. We can also write this equation differently. We can write it using function notation. So instead of the y, we can write f of x equals x squared. So the y and f of x are pretty much interchangeable. And this is what we call function notation. And you read this aloud, f of x equals x squared, or if you have a different letter, g of x. It does not have to be f. So if you're thinking, oh, function notation starts with f, that's why we use f. You can use f, you can use g, sometimes you'll see h. There's all kinds of different letters, but I would say the more common ones that you'll see are f and g, but it doesn't have to be those letters. And we call the independent variable is sometimes called the input, and the dependent variable is sometimes called the output. So let's do an example. Let's write this equation in function notation. This one is a little bit longer than the one above. So in the one above, we had y equals x squared, and all we did was we replaced that y with a f of x, and we were done. We got the function notation. Well, we could do the same thing here, but really we want the f of x by itself on one side. And notice that the y is not alone. It's got that 3x with it too. So what we're going to do is we're going to solve for y. And then we're going to replace y with f of x. So let's write down 3x minus 2y equals 6, and I'm going to solve. I'm going to get y by itself. So I'm going to take off 3x from both sides. So I just tack that 3x on the end because 6 and 3x are not like terms, so I don't combine them. I don't combine that 6 minus 3. And then I want to get y by itself, so I'm going to divide by -2, and I'm going to have to divide all of these pieces by -2. So then I get -2 divided by -2 is 1, so I get y equals, or 1y, but I don't have to write the 1. 6 divided by -2 is -3. A negative divided by a negative, this changes to a positive. And then 3 over 2, I could just write 3 halves x. And so that's the equation. And if you wanted to write the 3 half x first, you could. There's nothing that says that I have to do it in this order. But now what I'm going to want to do, so this was step 1. Step 2 is just to replace that y with an f of x. So f of x equals -3 plus 3 halves x. Or you could also write it 3 halves x minus 3. So all of these versions would be acceptable on Connect. So there's always going to be a couple different ways you can put it in, and you should get the right answer either way. So hopefully that makes sense in terms of function notation. So now that we've talked about that, let's talk about how to evaluate a function. So evaluate means you're given an x value and you want to figure out what the y is. So basically this is what I call plug and chug. You plug it in and you work the problem out. So let's do an example. So we've got two functions here, f of x and g of x, and the reason that we use those different letters is because it's easier to refer to different functions that way. So when we do, when we're asked to evaluate, for instance, f of 3, that's how we say this, we know, oh, that means to plug 3 in for the function that has the f. So I'm going to plug 3 into this. I'm not going to plug 3 into the one with the g. So I'm going to plug 3 everywhere I see an x, and I'm going to evaluate. So 3 squared is 9, and you're going to use your order of operations. 3 times 3 is 9 minus 5. So I get 18 plus 5, and I end up getting 13. Okay, let's do another one. So let's do f of -2. This is one I want you to pay close attention to, because when you have functions where you have a squared key, this -2, it can sometimes be tricky. So our function is x squared. So if I have a -2 squared, I want you to write it like this, and I'm going to use a different color here so it's really clear. If you're using a calculator, I want you to make sure to put parentheses around that. Okay, so plus 3 times -2 minus 5. And here's why. When you square -2, really what this wants you to do is this. And if you don't put parentheses, you're going to get the wrong answer. So negative 2 times negative 2 is a positive 4, plus 3 times negative 2 is negative 6, and then minus 5. And if we did that with a calculator, but we didn't put parentheses, let me show you what would happen. I'm going to use the TI-30 for this one. So if I just did negative 2 and then the squared button, watch what happens. I end up getting a negative 4. If I use parentheses, then I end up getting a positive 4. So if you don't write it down right, then you're going to put it in your calculator wrong, and then you're going to get the wrong answer. If you do these by hand, then you will likely get the right answer. So 4 plus negative 6 is negative 2. Negative 2 minus 5 is negative 7. So the answer there is negative 7. So now I'm going to try some with g. So I've got g of 0. So I'm going to plug 0 in for x. And then with order of operations, you'll treat the square root kind of like parentheses. So you're going to want to do this first. So 4 plus 0 plus 1 is 1. And then the square root of 1 is just 1. And we add those together and we end up getting 5. And then let's do one more, g of negative 3. So that leaves me with 4 plus the square root of negative 3 plus 1. So let's do the inside of the square root. Negative 3 plus 1 is negative 2. Now here's where you have to stop for a minute. Anytime you get a negative under the square root, you're going to get an answer that's undefined, and here's why. Think about this for a minute. So the square root is asking you, is there a number when you multiply it by itself you get negative 2? And that would be impossible, because the same number when multiplied with itself, you're never going to be able to get a negative there, because a negative times a negative is a positive, and a positive times a positive is a positive. And if you're not sure, you could very easily use your calculator, press the square root button, try to do the square root of negative 2, and you can see there's an error. So when there's an error like that with the square root, it means that what you're trying to take the square root of, that's not possible. So we're going to write undefined. And that'll be an option in Connect as well for an answer. So the next part, I think this is probably the most challenging concept in this module. It's domain and range. And just like with the functions, you can look at domain and range by just looking at trying to figure it out based on the function itself, or you can look at the picture. I find more people have better luck with the picture, but definitely, I'm going to show you both ways, and you can tell me or you can decide which way is better for you. So the domain of a function, that's this first blank. The domain of a function is the set of all values of the independent variable x. So the key is independent variable x that result in real number values for y. I also like to think of this as the acceptable values for x. Okay. The range, so that's the next blank. So the range here is a range of a function is the set of all possible y values or acceptable y values, either one. So I always remember D comes before R in the alphabet, so D goes with the X, R goes with the Y because X comes first. Just a silly little way that I've always thought about this to help myself remember that domain always has to do with the X, range always has to do with the Y's. So let's look at this first function. So y equals x squared. So, and you can write it like that if you need to. Remember the function notation, that's just y. So if you want to write it with a y, you can. So the domain here is, are there any x values that you could not square? Ask yourself that. Try to find this counterexample. Are there any x values that you could not plug in here to square? And the answer is no. You can plug in anything because it's totally fine to square whatever number you want. So I'm going to say x can be anything. So domain is all real numbers. The thing is, though, is you're going to be asked in your homework to put your answers in what we call set builder notation. And what you're going to want to do is you're going to have to do a curly bracket, an X, a vertical line, and then you're going to write some sort of description here that describes what that x needs to be. And this is for domain with the x. For range, we're going to use a y. So in this case, x can be all real numbers. So the way that we can write this is the set of all values, that's that curly bracket. We put an x, we put a vertical line, and what we could do is put a negative infinity less than x less than infinity. And what this says is x can go anywhere from negative infinity to positive infinity. It means that x can be anything. So this is how you put your answer into Connect. And then keep in mind that the keyboard, you have the curly brackets on a computer keyboard, and then the curly brackets will also be on your Connect like math palette that pops up, and so will those little infinity signs. So, and then let's look at, before we do range, let's just look at the graph real quick. So I'm going to go to Desmos, and I'm going to type in y equals x squared, y equals x squared. And for the domain, we're looking at the x's, and we're looking to see when I look left to right, because the x's are on this horizontal axis down here. When I look left to right, are there any x values that this function would not contain? And I know it's hard to see, like if I asked you, like, you know, is there an x of negative 100? Now right now on the screen I can't see that because it only goes to a little bit after negative 10. But is it possible? And the answer is yes. Like if you kept moving it sideways, this graph keeps going on and on and on and on forever in that up left direction. So eventually it would. So there isn't any x values here that I can see that this function would not be possible for. So with range, okay, that's a little different. So you've got to think, okay, well, I can put any x's in that I want, but are there any y's that I would not get? And this one's really a lot easier to see on the picture. So let me pull that up. Do you notice that when you look at this picture, the function starts here at the x-axis and it goes up? There's nothing down here below the x-axis, and nor there won't be, because the function is heading in the upwards direction on the left and right. So for the range, okay, that has to do with this vertical, so we're looking vertically. The smallest x value or y value that we would ever get would be 0, because that's where it starts, and then from there all of the points on this graph increase. So like this point right here is 1, 1. This point right here is 2, 4, and so on and so forth. The other way that you could look at it is look at the equation. So when you plug the smallest, even if you plug negative values in for x, they're always going to end up being positive because you're squaring it. If I plug 0 in for x, that would be that's the smallest number possible. That would give me a 0 for y. And so my range here, since y will never be negative, the way that I write my range is a curly bracket, and we say all values of y such that y needs to be greater than equal to 0. So, and this is because y will never be negative. Okay. So let's look at the next one. So I've got 3 different types of examples, and I picked these on purpose because I think these are these match up with your homework questions really well, and these also show functions that sometimes have some issues, so they're worth talking about. So in this next one, we've got a square root. So I want you to think about, when we've got square roots, is there anything that could happen with a square root that might yield like an undefined result? We dealt with that earlier, okay? So let's kind of think about that. So let's start with domain. So what x's are allowed? Can you plug in anything for x? And with a square root, the answer is no. You can't have a negative square root. So we want x to always be positive. So I'm going to write the domain as all values of x such that x needs to be greater than or equal to 0. And then for y, or my range, if x can only be 0 or more, this is where you could plug in a couple values if you need to. So what if x is 0? If x is 0, then you end up getting a y of 0. If x is 1, you end up getting square root of 1 is 1. If x is 4, I'm going to pick values I know the square root of. You get y is 2. If x is 9, you end up getting a y value of 3. So notice what's happening with these y values. It looks like they're greater than 0 too. And what we can do is we can check on the graph here, and we can do the square root of x, and you can see that the x's start at 0 and they go to the right, and then looking up and down, so that would be my y, the smallest y that we have is 0, and then they increase from there. So the domain and range are actually the same. The only difference for the range is we're going to write a y, and then y is greater than or equal to 0. Okay, so the answers that you're plugging in connect are these set builder notation answers. Okay, all right, let's do one more. So this last one, we've got a rational function. So it's a big fraction, and I'm going to start with domain and ask yourself, is there anything that we couldn't plug in for x? And we've got x in more than one spot. So we've got an x in the numerator, an x in the denominator. And here we want to think about a fraction. So with a fraction, is there anything that we couldn't have in a fraction that would produce an error, like in a calculator, for example? And the answer is yes. You don't ever want the denominator to be 0. So this denominator can't be 0. And so when you're trying to figure out, well, what x is not allowed, ask yourself, what x would allow this denominator to be 0? What plus 1, so you could even solve an equation if you wanted to, what plus 1 equals 0? If you solve that, you end up getting -1. So -1 would not be allowed. So for your domain, you would say all values of x such that x cannot be -1. That would be your domain. That's what you would plug in to connect. And if you look at the picture for that, so I'm just going to go ahead and graph that. So now this calculator doesn't have a fraction button, so I'm going to have to use parentheses and do 3x minus 2 in parentheses divided by, oh, it looks like it formats it like that. That's awesome. X plus 1. And notice, looking at the x's here, we said that x can't be -1. Look at x's -1 is right here. And if we look up and we look down, you see how this graph gets, it actually gets really, really close to -1, but it's actually never going to touch it. So that just confirms that we've got the right answer. And then for our range, we can ask ourselves, we can look for a contradiction. So what we can do is we can also look at the graph. And I think the graph is probably the easier way to start with this one, because algebraically it's a little bit harder. If you look at the y values, so by y you can actually start drawing horizontal lines here. I know you're thinking horizontal, that's usually x, but I'm just kind of moving my way up vertically to see, are there any y values that this function is not going to hold? And do you notice that when we get to y equals -3, if you were to draw a line there, that this function doesn't ever touch y equals -3. Like if we look this way, it gets so very close, but it doesn't touch. And then we look this way, it's going to get so very close to y equals 3 and it doesn't touch. This y equals 3, it's actually called an asymptote. And algebraically, if we were to solve this, if we were to say, well, what happens when y is 3? And we were to solve this, you could solve this a couple different ways, but one way would be to multiply both sides by x plus 1. So if I multiply this side by x plus 1 and this side by x plus 1, that would go away, and we end up with 3 times x plus 1 equals 3x minus 2, or 3x plus 1, or I'm sorry, 3x plus 3 equals 3x minus 2. If I take off 3x from both sides to try to get the x's together, what happens is they both end up canceling out, and I left with this statement 3 equals -2, and that's a contradiction. That's false. That 3 does not equal -2. So when I have a y value of 3, it ends up with a situation that just doesn't make sense. And so my range for this example is going to be all values of y such that y is not equal to 3. And like I said before, I think the algebraic, what I did here, I think that's easier to see once you look at the graph. That would be, rather difficult to kind of jump there in the beginning, but I would definitely, for one like this, just try to look at the picture and see if there are any x and y's that this graph does not end up basically touching. Okay, so we're gonna move on. We're gonna talk about some different types of functions. And like I said in the beginning, we're just gonna touch on these pretty briefly. So we're gonna start with linear functions. So linear functions are commonly in the form y equals ax plus b, or you may know this as y equals mx plus b. It doesn't have to be in that form. So any time an equation has just an x or just a number, so like for example, y equals 3x or y equals 5, it actually doesn't even have to have a number, or have an x, or it could be like y equals 3x plus 2. Anytime when graphed, the function makes a straight line, we call it a linear function. And there are lots of different ways to graph these, and if you were to take an algebra class, you might spend several weeks talking about graphing. We're not going to do that here. We're just going to touch on the important parts. So a couple different things that you could consider. One thing to consider is you could and that's the second option. You could pick 3 or 4 numbers, any numbers, plug them in for x to find y. This always works for graphing, no matter if it's linear or if it's a different types of function. So for example, if I take a, this first function, f of x equals 3x minus 2, I'm actually just going to put a y there instead of the f of x. And then I make a table of values. I could pick a couple of x values, plug them in, and find y. So for example, I might pick -2, 0, 2. I like to pick 0 because it's easy to plug in, and then a negative and a positive. And then all you have to do is plug it in. So you're going to do 3 times -2 minus 2. So we've got -6 minus 2. That gives me -8. If I plug in 0, 0 minus 2, I get -2. And then if I plug in 2, I get 6 minus 2, which is 4. And then I go ahead and I just plot these points. These are just ordered pairs. So -2, -8, 0, -2, and then 2, 4. And if I did this right, they should line up to be a straight line. And so you're going to want to just use a straight edge and connect those lines. That's one way. If you're familiar with algebra, you can certainly do the first option where you use the y-intercept, which in this case would be -2. So you plot the y-intercept, which is -2, and use a slope of 3, which means go up 3 over 1, up 3 over 1, and that'll allow you to graph it as well. So couple different options there. For the second one, this would be a great time to pause the video and try this one on your own. So I'm going to write y equals 2/3 x plus 3. And I'm going to pick some x values. I'm going to do -3, 0, 3 for this one. And I'm picking these on purpose because I know that I have a fraction here. And so if I plug in -3 or -3 over 1, that allows these to cancel and it makes for a really nice answer. So 2 times -1 is -2 plus 3. We end up getting 1. Okay, and then I'm going to go ahead and I'm going to plug in 0. So 2/3 times 0 plus 3, I end up getting 3. And then 2/3 times 3, or 3 over 1 plus 3. These cancel, and I'm left with 2 times 1 is 2 over 1 that's just 2 plus 3. And then I end up getting 5. So I have 3 ordered pairs, -3, 1, 0, 3, and 3, 5. And then I'm going to go ahead and plot those. So -3, 1, 0, 3, and then 3, 5. And Do I have to just do 3 points? No, you could do more. I mean, as long as you have a ruler, you don't need any more. The minimum you need is 2. I like 3 just in case you make a mistake, because if you make a mistake on one of your points, if you only pick 2 and you make a mistake on one, then you'll just end up with the wrong answer. If you do 3 points and you make a mistake on one of them, you're going to find out because you'll try to connect it and it's not going to make a line, and that is a good clue to you that you made a mistake. So I think good rule of thumb is to use 3 points, but you know, you can go ahead and choose. And then remember, we've got that graphing software, Desmos, for you to use to check your answer. So we're going to do some story problems, or one story problem, interpreting the graph of a function. So this is a story problem having to do with a linear function. So the graph of the function that represents the percentage of babies in the United States born to unwed mothers since the year 1970 is shown in graph below or to the side. Use it to answer the questions. So it says the percentage of babies, so that's going to be on your y-axis. So this is percent of babies. And it says years since 1970. So that means 1970 corresponds with the origin or 0. So this would be 1970, and this would be on the x-axis is year. So if 1970 is equal to 0, then 10 years later, this would be like 1980, 1990, 2000. And I'm just adding 10 years each time. So it would be a good idea to go and label this before you start answering questions. It says about what percentage of babies born in 2005 had had unmarried mothers. So in 2005, you want to think about how many years after 170 or 1970 is that? So 2005 it's 35 years after 1970. Okay, so basically we're trying to find it'd be like an x value of 35, which is right here, or you can see it'd be between 2000 and 2010. So you can use the blue numbers that I did in the beginning, or between 30 and 40 there. And so if we go up, you want to find what y value that corresponds to on the graph. So it looks like it meets it about there, and then you're going to come over here. And this is not an exact science here. You're going to just do your very best when you're looking at it visually. So visually, it looks like maybe 38, but then notice here they give you an equation. So if you're given an equation, then you should actually plug that in to find out the real answer and to verify that your eyeballing was correct. So I'm going to plug in 35, and I'm going to do 0.773 times 35 plus 10.925. And if I do that, I end up getting 37.98. Which is about 38%. And then just pay attention, like on connect, it'll tell you to round. Like in this one, I think it says round to the nearest whole number. So we'd say it's 38% there. And then let's look at B. So about when did the percentage go above 25? So let me go ahead and erase this. So let me draw a line where the percentage of 25 would be. So it looks like about there. Okay, this looks at about 25. And if we look down, we can look approximately, pretend that line is straight. You know, eyeballing it, it looks like maybe, I don't know, 16 or 17, but remember you have the equation. So there's no reason to just eyeball it. You should actually write out the equation. So in this case, the 25%, that's going to be the y variable. So what you can do is you can put in a 25 here and solve this for x. And just to be clear, because I know sometimes students will make this mistake on this one, if it's 25%, we actually just put in a 25. We don't put 0.25, and the reason is because if you look at the y value numbers, there aren't any decimals on those. Those are just the percentage numbers without the decimals, so I want to use that same type of number when I plug it into the equation. And then I'm plugging that in for y, because the percentages are the y variable, and then I'm going to solve for x. So I'm going to take off 10.925, and then I get 14.075 equals 0.773x. I divide both sides by 0.773x, not by x, sorry, 0.773, just the number, so that goes away and x is left by itself, and I get approximately 18.2082. I'm just going to write down the full answer here, and then you'll want to make sure that you go ahead and round that to whatever place value that Connect asks you to. Okay, so the next piece with linear equations, and this will be the last thing we do with linear, is writing and using functions. So let's look at this example. So we've got a company determined its price per unit is $73.50, and anytime you see that word per, I like to pay attention to that. That usually is referring to the slope or the number in front of x, divided by the product of 0.05 and the number of units it sells. So let's write the price per unit as a function of the number of units it sells. If P is the price per unit, so that's your output variable, and X is the number of units sold, that's your input. So I'm going to start by saying P of X, and I'm going to write down an equation. I'm going to read it again and write down the equation as I'm reading. So the price per unit is $73.50, so I'm just going to write down $73.50 divided by the product, okay, so that means times, of 0.05 and the number it sells. So 0.05 and the number it sells. And so that's the equation. And so in this case, the 73.50 itself, that actually isn't just the slope, the part in front of x. This is actually, the x is on the bottom, so this actually wouldn't even be linear here, but this would be our equation. So we would leave it for that, like that, and then the next part, use the model to determine the price per unit if the company sells 3,000 units. So they're giving you the number of units. So this is where I'd ask yourself, well, what variable is that? That's going to be your x, and so I would plug that in. So we say P of 3,000, that just means plug 3,000 in for x, is 73.50 divided by 0.05 times 3,000. So we're just plugging it in. And where I'm writing it here, this is just the notation. This doesn't mean anything on the left. Like, I'm not doing any math there. That's just the notation that says, hey, we're plugging 3,000 in. So all the math is going to come over here. So you're going to do, you can put this in your calculator and you should get 0.49 or 49 cents per unit. So that's the answer for that one. Okay, so let's look at section 6.5. So 6.5 is on quadratic and exponential functions. They are not linear. Let's start and talk about quadratic. So this is going to be just the important parts, just a quick review or overview of what a quadratic function is. So the graph of a quadratic function is a parabola, and a parabola is a graph that looks like a U. So it's either usually facing up or it can be facing down. And the graph oftentimes takes this form, but not always. The key here is that there is an x squared somewhere in the graph. There may be an x, but maybe not. It's not necessary. There may be a number like the C. There may be not. It's not necessary, but there's got to be an x squared, and there can't be anything more than an x squared. Like if there's an x cubed or an x to the fourth, that would not be quadratic. So let's go ahead and we're going to go into this first example where we solve a quadratic equation. So, and this could be handy in story problems where we want to find the value of x when y is equal to some number, kind of like similar to what we just did in the last example, only this is a quadratic function instead of, the other one was not. So there's two methods that you can solve a quadratic equation, and just like before, I mean, you could spend, 2 months on this, like in an algebra class. I'm just going to show you these real quick. And you can also look at the graph. So if you don't want to do these by hand, you can completely avoid this and look at the picture, and I'll show you how to do that as well. So you'll have some tools here to use so that you don't have to go back and basically relearn all of algebra. So One way to do this is to solve by factoring and using what's called the zero product rule. If you remember how to factor from taking algebra in the past, then I think that that's great and this is a great option. If you don't, then I would say skip this method and move on to either the next one or graphing. And so factoring basically involves you take we say factors because there are these two expressions that are multiplied, and we try to figure out, we put an x here and an x here, and you may remember that when you multiply these, we use, it's called FOIL, first, outer, inner, last. So when you multiply the first two terms, you end up getting that x squared, and then we're going to multiply the outer, and we're going to multiply the inners, and we are going to multiply the last two terms. And together, when we do all of that multiplication, we should end up with x squared minus 12x plus 20. And so we're trying to figure out what two numbers multiply to give us 20, but add to give us negative 12. And so you've got a couple of options, like with 20, you could do 1 times 20, you could do 2 times 10, you could do 4 times 5. And then again, you want these to add to give you negative 12. So I would put negatives with these. A negative times a negative gives you a positive, but when you add them together, we want to find which ones have the sum of negative 12. And the ones that have the sum of negative 12 are negative 2 and negative 10. So those are going to be the numbers that we're going to put inside the parentheses. So if we do x minus 2, x minus 10, let's go ahead and do our FOIL, first, outer, inner, last, to see if we get our original equation. So x times x is x squared. First, outer, x times negative 10 is negative 10x. Inner, negative 2x. And then last, positive 20. And if I combine those two middle terms, I get x squared minus 12x plus 20, and so that ends up working. And then at this point, once you've factored, the way that you solve, I'm going to go ahead and erase this so I have some more room, is you write down your two factors, x minus 2 times x minus 10 equals 0, and you use, it's called the zero product property, where you set these both equal to 0 and you solve. And so you solve this and you get 2, you solve this one and you get 10. Okay, and so on a graph, what that would look like, if you have a parabola, it means that the parabola is going to cross the x-axis at 2, and it's also going to cross at 10. And so if we pull up, I'm going to pull up Desmos real quick, and let's go ahead and put this in. So x squared minus 12x plus 20, you can look at the x-axis, and this is awesome because it shows you really clearly it crosses at x equals 2 and x equals 10. So those are your solutions here. So you could have just completely avoided this altogether, this work, and just graphed it. So if this is overwhelming to you, I would say totally skip it and just do the graph. Same with the second one. So I'm showing you these just as options, but you don't have to do it this way. So if you're okay with the visual graphing, then that can be a good option. So the other option is using the quadratic formula, which is right here. And the quadratic formula uses the standard form of a quadratic equation where a is the number in front of x squared, b is in front of x, and c is a number by itself. So if you look at our example up here, a is the number in front of x squared, so a is just 1 because there isn't another number in front of there. B, you got to make sure that you include that negative 12, so b is negative 12. And c is going to be the number added to the end, which is 20. Then all you have to do is plug them into this formula. So negative 12 plus or minus the square root of negative 12 squared, make sure you put parentheses there, minus 4 times a times c all over 2 times a. And then we're going to go ahead and we're going to simplify the inside there. So if we do, we end up getting 12 plus or minus the square root of 144 minus 80 over 2. And then I'm going to keep simplifying. So 12 plus or minus root 64 over 2. Square root of 12, square root of 64 is 8. And then the plus or minus means you need to do two problems. You need to do 12 plus 8 over 2 and then 12 minus 8 over 2. And if you end up doing that, you end up getting 10. and 2. And so those are your solutions. And again, on the graph, you could have just graphed this at the very beginning and saw that where that graph crosses the x-axis are the solutions for when this function is equal to 0. So 3 different ways. I would just pick which one makes more sense to you. So graphing quadratic functions. So the graph of a quadratic function, I've already mentioned, but it's called a parabola. Okay, and that's this U-shaped graph. The axis of symmetry is just this invisible line that divides it into 2 separate halves because these halves it's symmetric. So in knowing that it's symmetric actually can help us graph quite a bit. We have what's called a vertex, which is the point either at the very bottom or the very top. So that's helpful. And then notice the parabola is going to face up if that leading coefficient, which is the number in front of the x squared, if it's positive, it's going to face up. If it's negative, it's going to face down. So that can kind of help you just check if you're on the right path for graphing. So I've got some instructions here in the box for how to graph. There's different options like I've shown you before. I think that the easiest way is to find the vertex and to pick some values on either side of x. And actually with the graphing software we have, if you were able to just put this in the graphing software, you could also graph it that way. But I'm going to show you how to do it by hand. So the formula for finding the vertex, it's actually right up here, is negative b over 2a. That's the x coordinate of the vertex, and then you have to plug that into the equation to find the y value of the vertex. So I'm going to go ahead and do that. So we have this function here, and our a value is 1, our b value is negative 6, and our c value is 5. So I'm going to find the vertex by doing negative b over 2a, so negative 6 over 2 times 1, or 6 over 2, and I get 3. And then I'm going to plug that in. So I'm going to do 3 squared minus 6 times 3 plus 5. And when I do that, I get negative 4. And so the vertex at this point is 3, negative 4. And so I plot that 3, negative 4, 1, 2, 3, 4, and that's my vertex. And then I can look at the graph. The leading coefficient is positive, so I know it's going to face up, but I don't know how wide or how skinny it is. So what I could do is I could just plug in an x value. So maybe I could plug in, I don't know, maybe 0, because that's an easy one to plug in. So if I plug in 0, so if I plug in x equals 0, I get 0 squared minus 6 times 0 minus 5. So I get 0 minus 5, so I end up getting negative 5. So that means the point 0, negative 5 is on the graph. So I'm going to go ahead. Oh, and you know what? I did that wrong because I'm looking at it. If it was 0, negative 5, it would be down here, and I just said that this is a face-up graph, so I must have done something wrong. So let me go ahead and look. You know what? I wrote down minus 5, and this should be a plus. There you go. So just knowing the general shape of the graph, see how that caused me to fix my mistake there, because I knew that it should be facing up. So 0, it should be 0, positive 5. I'd like to say that I did that on purpose to show you, but I did not. So 0, 1, 2, 3, 4, 5 is right there. Now the cool thing about parabolas is they're symmetric. So if you go over 2 or over 1, 2, 3, up 1, you can go from the vertex, you can go 1, 2, 3, up 1 on the right side without doing any other work. So that gives you a good general idea of how to graph. Now, there's other methods, like I said, you could do more points if you wanted to, but that is, you know, I think that that's a great starting off point just for this class. And then don't forget too, you can always use the graphing software Desmos to double check your work. So let's try some story problems with some quadratics. So this first one, we've got a model of percentage of the population where X is the number of years after 1900. So pay attention there. When you've got problems like that, it just makes it a little trickier. So we're going to say X, we're just going to highlight that so that way we are aware of it. So part A, when did the percentage reach its low point? Anytime you have a quadratic, remember that's a parabola, either facing up or facing down. In this case, the A is positive, so it's going to be facing up. If we want to know the low point, that's going to be talking about the vertex. So this question is basically just saying, find the vertex. So we're going to do x equals negative b over 2a. That's the formula for the x value of the vertex. So in this equation, my a is that 0.0033. This is b, this is c. So I'm going to do negative 0.420. Notice negative is in the formula. So if b is negative, you've got to account for both of those negatives there. Divided by 2 times a, 0.0033. And when I do that, I get 0.420 divided by 0.0066, and I end up getting 64. So that means the vertex is 64, comma, we don't know. But it's just asking when. And remember the x value, that's years. So I don't even need to find y. That would be the population or the percentage of the population. I don't even need that because it doesn't ask for it in this question. So I'm going to say 64 years after 1990. And so if I do the math on that, or not 1990, 1900, so that would be 1964 would be my answer for that one. So the next one, when was the percentage? What was the percentage? So what was the percentage? We're looking for y in 2012. So we have to figure out, well, how many years after 1990 or 1900 is that? So from 1900 to 2000 would be 100 years. And then in 2012, that'd be another 12. So this would be like x equals 112. So all this is saying is plug 2000, find p of 112, find p of 112. So we're going to take our equation and plug in 112. And then if we plug it in and we do all the math on that, we end up getting about 13.9%. And I didn't tell you how to round in this, so I'm just going to approximate it like that. Just pay attention when you're doing your homework. You should have rounding directions there. And then for C, if the model accurately predicts future trends, what will the percentage be in 2020? So you'd have to figure out, well, what is the x there? So that would be x equals 120 because that's 120 years after 1900. So you do the same thing as we did earlier. We just plug in 120. So if you plug in 120 to the equation, you end up getting about 16.6. So 16.6% about there. Okay, so we've got one more story problem for quadratics, and there's one like this in the homework, so I definitely want to get to this one. So projectile motion function. So we've got this is a general function that you can use anytime you've got projectile motion, which just means that something is being thrown up in the air or thrown in general. And I just want to point out, so this v, we call it v naught or v sub 0. This is initial velocity. You're going to need to come back to this later because in your homework you're going to also use this. And this h sub 0, that's your initial height. So as you read the problem, I want you to jot those down because we're going to need to plug those in. So if a bowling ball is launched upward from the top of a 230-foot building, so if you have this building, and this building, we'll say is 230 feet tall, and you've got a bowling ball, it's going to be thrown up. Okay, if it's thrown up, it eventually will come down. So you can see that that curve looks like part of a parabola. It has initial velocity, so I'm going to write v sub 0 is 60 feet per second. Find the maximum height and how long it takes to reach the ground. So we weren't specifically given the initial height, which we need, at least it didn't say it in those words, this is the initial height, but we were given the height, and the height is 230 feet. That is the initial height of the bowling ball. So h sub 0 is 230 feet. So I'm going to go ahead and write this function, but instead of v sub 0, I'm going to write 60, and instead of h sub 0, I'm going to write 230. So just to be clear, I put the 60 and the 230 in myself. Those were given in the problem. The rest of the numbers are given to you. So the first question, it says, is find the maximum height. Anytime you want to find the maximum height of a parabola, that's going to correspond to the vertex. So let's go ahead and find the vertex. So to find the vertex, we're going to do negative b over 2a. So in this case, my b is 60, so negative 60 over 2. My a is negative 16. So I'm going to go ahead and calculate that, and I end up getting 1.875. Now this is going to be my x value of the vertex. So the vertex is a coordinate pair, so 1.875, that's the x value, and it says that the input in this case is going to be would be time, because if the velocity is 50 feet per second, this would be seconds. So it means that after 1.875 seconds, that bowling ball is at the highest point in the air. But notice it didn't ask the time for the maximum height, it asked the maximum height. So we actually have to plug that into the equation to find the max height. So I'm going to take negative 16 and I'm going to plug in 1.875 to the equation. And I end up getting 286.25. So max height is 286.25, and we know it's feet because the velocity was 60 feet per second, and that occurs at 1.875 seconds, but they didn't ask for that, so we just stopped there. And so that's the first part. And then the second part, how long does it take to reach the ground? Well, when it reaches the ground here, the height is going to be 0. So basically that's like saying, when is height, or in this case it would be h of t, equal to 0. So we're going to plug 0 in for h of t and we're going to solve. So I'm going to plug 0 equals negative 16t squared plus 60t plus 230. And this is where you have a couple of options. You could factor, you could use the quadratic formula, or you could go ahead and use your graph. So one way is just to plug it in. So I'm going to just type in 0 equals negative 16. Now in this case I'm going to use x just because that's the input variable that the system uses. It'll give you the exact same graph as putting a t there. And so we can see, I'm just going to zoom out here. Whoops, actually maybe what I can do is maybe I should zoom in. There we go. Okay, and so again, we're looking for when the height is 0. So the height is 0. There's two options here. So the height is 0. We've got two options, negative 2.355 and 6.105. You have to choose. Now keep in mind that the x value represents seconds, time, so it doesn't make sense to have a negative time. So I'm actually just going to ignore that one. And my answer is going to be 6.105 seconds. So 6.105 seconds. And it is totally fine to use the graph like that. And if you use the quadratic formula, you would end up doing the work and you would end up getting those two answers. And the other one was negative 2 point something. And you would just cross off that negative one because it just doesn't make any sense given that time can't be negative. So I hope that makes sense, but definitely let me know if you have any questions. All right, so let's go ahead and talk about exponential functions. So we're going to do some quick graphing and then we're going to do some story problems. So exponential functions are functions that look like, I'll just give you a general shape. So they look like either like this or like this. And you may have heard the term exponential growth or exponential decay, and that's just referring to, you know, when something grows really rapidly or when something shrinks or decays really rapidly. And so the form of this equation is this right here. So C is just a number, and A is a number, and the exponent is x. So there's a couple things about this graph. When the a value, we call that the base, when it's greater than 1, the function's increasing. So for example, if you add the function f of x equals 3 to the x, that's going to be an exponential growth. If the a value is less than 1, so if it's like f of x equals 0.5 to the x, then it's going to be exponential decay. It's going to be decreasing. And then it does have a horizontal asymptote, which just means that it never touches the x-axis. It gets really, really close to the x-axis, but it doesn't ever touch. So how do we graph? Very similar to the other ones. We can just pick some x values, plug them in, and then find y. And then you have your graphing software, the Desmos, to double check. So let's do this first one. So we've got f of x equals 2 to the x, and I'm just going to pick some x values here. So I'm going to pick -2, 0, 2. So if I plug in -2, I get 2 to the -2 power. And you could certainly use a calculator for that if you need to. This means 1 over 2 squared. When you have a negative exponent, it just tells you to put in the denominator, which is 1/4. So the point here, if we look at the coordinate pair, so this is your y value is 1/4, but the coordinate pair is -2, 1/4. So that's your first point. So -2, and I'm just going to go up just a tiny bit, 1/4. And then if I plug in 0, 2 to the 0 power, anything to the 0 power is just 1. So the point there is 0, 1. So 0, 1. Oh, and it looks like that one disappeared. There we go. And then if I plug in 2, 2 to the 2 power, you get 4. So 2, 4. So if you want, you can keep going, but your graph is just going to look like this. And then remember, there's that horizontal asymptote there, which means that this graph gets really close to the x-axis, but it doesn't actually touch. And then the second one, notice that there's a fraction here, so that's going to be a decay. So I'm going to go ahead and pick some x values. And I'm just choosing, I'm going to pick the same ones, -2, 0, 2. Those aren't, the best x values to pick. I'm just picking them, and you can choose to pick more if it makes the graph more clear to you. So for this one, I've got 1/2 to the -2 power, and you could certainly use a calculator if you need to. That's going to be 4. And so that gives you the point -2, 4. 1, 2, 3, 4. And let me show you, what I'm going to show you real quick on the TI-30 how to put that in the calculator. You could use your fraction button, and then you could do, so 1/2 come out of your fraction, and then just use the exponent key, and then you're going to type in -2, and that gives you your answer of 4. And then 1/2 to the 0 power is just 1, so that gives you the point 0, 1. And then 1/2 to the second power is 1/4. And again, you could use your calculator if you need to, or actually write that out, 1/2 times 1/2, and multiply fractions that way. So this is a big module. So I think that if computing this is not your strength, it's totally fine to use a calculator. So I'm just going to plot those points. So 0, 1. And then 2, 1/4. And then, if you want to do more, then that's great. It gives you an idea, but I think this is okay too. And this is totally adequate in terms of being able to do your homework. So let's just go ahead. We've got 2 more problems here. I know this is a long video, but I want to get these done too. So we've got 2 story problems. And this first one, it gives us this function to model population. And notice you've got this a sub 0 here. It's the population at time 0, which just basically means initial population, like when we're starting this, when we're starting this investigation. So the problem says the population in 2007 reached 2 million for the first time. So let's let that be our initial population. So we'll say 2 million is our initial population, and that's starting at 2007. So that's where we're starting this function. It says use the model to predict the population in 2027. So if x equals 0 corresponds to 2007, then we need to figure out what x corresponds to 2027. And since it's 20 years later, then that would be x equals 20. So basically, all we have to do is plug 20 in for t. So we're going to do 2 million times 1.04 to the 20th power. And then I'll show you how to enter that into the calculator. So we're going to do 2 million. So we got 6 zeros, 4, 5, 6, parentheses, 1 point, whoops, missed that decimal there, 0.04. And then we're going to do exponent key, and then we've got the 20. And then there's your answer. So I'm just going to write down on my notes. So it looks like we've got 4,382,246 people. And then always ask yourself, does it make sense? This A value, it's bigger than 1, so there should be growth. So it makes sense to me that we started with a population of 2 million and then it grew quite a bit in 20 years, which is what you would expect. And then the last one, we're going to look at the compounding interest formula, because that's also an exponential formula because we have a variable in the exponent. So this says if $10,000 is invested, so that's our principal. So remember back from module 2, so $10,000 is our principal. It's invested in a rate of 8%. So if the rate is 8%, then that corresponds to 0.08 as a decimal, because we're moving our decimal 2 spots to the left. And then it's compounded quarterly, so that means our n is 4. And you can go check out the module 2 notes if you want to refer, if that doesn't ring a bell. And then we want to know the value of the investment after 40 years. So that would mean t equals 40. So remember, t is always in years. So I'm just going to plug all of those numbers in. So 10,000 for p, 1 plus my rate over my n times t, and then you can go ahead and just plug that into the calculator. And so remember, you can plug that in exactly how it looks. So if you've got the TI 30 or 34, you can plug it in. You can also do this on the graphing calculator. So I'm going to do parentheses 1 plus, I'm going to use the fraction key, 0.08 divided by 4, and then parentheses raised to the 4 times 40 power. And then you're left with $237,699. And if we round to cents, where it's going to be 7 cents, which is kind of crazy to think that's $10,000. You put in 10,000 and you get, over 200,000. So the power of compound interest. So let me just go ahead and write that final answer. So $237,699.07. Holy moly. Wow. All right, so we are done. I know that is a long module, so thanks for hanging in with me. Please let me know if you have any questions. I'm here to help.